In the previous lecture, I told you that it is fairly possible to have electrons lying between conduction band and valence band. Even though this gap is also known as forbidden band gap, but still there are fair chances of electrons being present there. Suppose that you have supervision which can see electrons even at crystal level. Now assume that there is a linear group of atoms above which there are electrons which are scattered near the boundary of the crystal. But this is the extent you can see. You would not be able to see any line there, neither the conduction band minima energy level EC, nor the maxima energy level of valence band EV, nor the Fermi energy level EF. These lines are reference energy, which we use to make our understanding easier. Likewise, we have assumed that EC is the minimum of energy of electrons which can be considered to be present in conduction band, increasing the conductivity of the semiconductor. But what is the significance of EC, EV and EF? Different students can have different doubts, and I have divided the complete analysis of Fermi Dirac priority function into three parts. The link for the first part is provided at the top. You should go through that. This is the second part, and after this lecture, we will discuss the last few points of the topic. Now we discuss about the significance of EC, EV and Fermi energy level EF. As you can see, the density of electrons is maximum in this region, which is nearest to the atoms. This means that the majority of electrons are strongly bound by the electrostatic force of the crystal and cannot be considered as free. Similarly, these electrons are those electrons which are at least trying to make transition to conduction band. Some of them will succeed while some of them will fall back due to insufficient energy absorbed. Talking about Fermi energy level EF, we have already described its significance in the previous lecture, that EF is the energy level where the probability of finding an electron is 1 by 2. Now, we will consider these topmost region electrons. These electrons are the electrons who have absorbed sufficient energy to make transition to conduction band, and we considered free from crystal's electrostatic force. When an external field is applied in the shown direction, then these electrons are the most mobile electrons that respond to the external electric field. I assume that it is clear to you that even though the middle region is called forbidden band gap, but still there is a finite probability of finding an electron in energy state between conduction band and valence band. But these electrons are the electrons which are not stable and are just trying to move to conduction band. Obviously, electrons does not know priorly if the energy absorbed has sufficient energy to make transition. If the absorbed energy is sufficient, then electron makes transition, and if the energy absorbed is not sufficient, then it falls back to the valence band, emitting quasi-particles like photon and phonon. Now we will roughly plot Fermi Dirac priority function at different temperatures and will observe the variation which will come in the graph when the temperature is increased. Here EFI is representing the intrinsic Fermi energy level, EF represents Fermi energy level, and I is representing intrinsic. In this lecture, we will plot the function for intrinsic semiconductor only. In the plot, on the y-axis, energy is represented, and on the x-axis, Fermi Dirac priority function is represented with maximum value of 1. Obviously, the probability cannot be greater than 1, and also it cannot be negative. At 0 Kelvin, we know that all the energy states below intrinsic Fermi energy level will be completely filled, whereas all the energy states above the intrinsic Fermi energy level are vacant. Now, suppose that the temperature is raised to some higher temperature, say T1, giving us a plot like this. In this graph, you can observe that few electrons have absorbed energy and are trying to move to the conduction band, but the temperature is still not high enough to provide sufficient thermal energy to electrons for making transition to conduction band. As you can see that probability in the conduction band is still 0, meaning that there are no electrons present in the conduction band. Electrons are able to reach up to this point only. Now, in the third graph, we further increase the temperature to T2 Kelvin such that the graph comes out like this. In this graph, you can see that there is a finite probability of finding electrons in conduction band. It means that few electrons have absorbed sufficient energy to make transition to conduction band. You should also notice that the Fermi Dirac probability at intrinsic Fermi energy level EFI is always 1 by 2. However, at 0 Kelvin, the Fermi Dirac probability value at Fermi energy level EFI is quite controversial, as it is just a theoretical value. You cannot observe it practically. But still, we assume that the probability value at energy level EFI is 1 by 2 at all temperatures, even at 0 Kelvin. Second important point is, obviously, this shaded area represent electrons, and these are the same electrons which are displaced from the energy states present below the Fermi energy level EFI. It means this area will be equal to this area. Now, I have a question for you. Since you already know Fermi Dirac probability function is a probability function, then will the area of the graph of energy versus Fermi Dirac probability function value be equal to 1? Or simply tell, is this area equal to 1 or not? This area will not be equal to 1. You may study in communication system as well as in engineering mathematics that suppose if you send data 1.1 through an analog channel, then due to noise, the data may get changed and can be received as any value between 0.9 to 1.3 with probability distribution as shown. It should be known to you that the area of this graph is equal to 1, as the sum of probabilities of all the possible outcomes of an event is always equal to 1. You can calculate area of this graph also. Area of this graph, which resembles the shape of a triangle, will be equal to 5 multiplied by 1 by 2 multiplied by 0.4, and this will give the area to be equal to 1. But students usually get confused in Fermi Dirac probability function as they consider it to be a single event, which is not true. You have to consider the occurrence of electrons at different energy states to be different event, and hence the area will not be equal to 1. Such questions becomes important for competitive exams as they are not covered in textbooks.